in the Great Pyramid comes from more than 500 miles to the south. If you look at the famous King's Chamber, its walls and its roof are, the ceiling of the King's Chamber are all made with gigantic granite blocks.
There is a room inside a modern research facility that, at first glance, has absolutely nothing to do with ancient Egypt. There are no glass cases filled with papyrus, no plaster casts of pharaohs, no dusty excavation journals stacked on wooden shelves. Instead, there is a scanning electron microscope surrounded by instruments designed for materials science, friction, wear, abrasion, and mechanical failure. The mystery itself, however, began much earlier. In the 1920s and 1930s, archaeologists were already documenting the extraordinary precision of Egyptian granite. By the 1970s and 1980s, researchers were debating how copper tools and abrasives could have produced such surfaces. Then, decades later, advances in microscopy and materials science opened a completely new way to investigate the ancient cuts. And one day, a small fragment of ancient granite, cut by human hands more than 4,000 years ago, is placed beneath the microscope's beam. The surface begins to reveal a story that cannot be seen with the naked eye. Buried inside the microscopic damage left by an ancient cut is a mineral that should immediately make anyone familiar with materials science stop and look twice. It is not simply sand. It is not the expected residue of a copper tool. It appears to be something harder, something capable of cutting materials that would have resisted almost every ordinary tool available to an ancient craftsman. And before we go any further, please subscribe to our channel and help us reach our goal of 5,000 subscribers. Because now, in the 2020s, inside a laboratory that was never designed to investigate the pyramids, an old question begins to open again. If this mineral really was part of the cutting process, then what did the Egyptians actually know about stone, hardness, and abrasive technology? That question matters, because the mystery of Egyptian stoneworking has never really been about whether ancient people could move enormous blocks. Human beings are extraordinarily good at organized labor, and given enough workers, time, ropes, ramps, sledges, and planning, astonishing quantities of stone can be moved. The deeper mystery lies in what happened after the stone reached the quarry. Most of the Great Pyramid is limestone, and limestone presents relatively few problems from a materials science perspective. It can be cut, shaped, dressed, and polished with comparatively simple tools. Granite is different. Granite is an igneous rock formed from cooled magma, and it is composed largely of quartz, feldspar, and mica. Quartz alone reaches about 7 on the Mohs hardness scale, far harder than copper. Modern engineers cutting granite rely on extremely hard abrasives, often industrial diamond, combined with powerful machines, constant cooling, and carefully controlled pressure. Even with all of that technology, granite remains difficult material to work. So when we look back more than 4,000 years and see enormous granite blocks, precisely fitted surfaces, carefully drilled holes, and highly polished stone, the obvious question is not simply, how did they move it? It is, what exactly did they use to cut it? For generations, the conventional explanation has centered on a deceptively simple idea. Copper tools provided the blade, while abrasive material did the actual cutting. The copper itself did not need to be harder than granite, because it could carry loose grains of sand into the cutting zone. Those grains, pressed between the copper and the granite, would gradually scratch and remove the stone. For rough shaping, ancient workers could also use harder stones such as dolerite, repeatedly striking the granite until the desired form emerged. On paper, the method makes sense. It does not require steel. It does not require electricity. It does not require diamond saws. It requires materials that ancient Egypt demonstrably possessed, combined with enormous amounts of labor and time. But there has always been a difficult question hiding inside that explanation. Can those tools and abrasives actually reproduce the remarkable precision visible on surviving Egyptian granite? That is where the controversy begins. Experiments involving copper, abrasive material, and granite have shown that the basic principle can work. Granite can indeed be removed using abrasive particles carried by a softer tool. But the process can also be extremely slow, and reproducing every feature of ancient Egyptian stonework is a much more demanding challenge. The question becomes one of scale, efficiency, surface quality, and, most importantly, the microscopic signatures left behind. If a particular abrasive was responsible for ancient cuts, then it should have left physical evidence. Scratches should have a particular geometry. Wear patterns should tell a story. Particles should become trapped inside microscopic fractures and grooves. And if scientists can identify those particles, they may be able to work backward from the finished stone to the technology that created it. This is where Graham Hancock enters the story. Hancock is not an Egyptologist or a materials scientist, and his broader interpretations of ancient history have been highly controversial. But one particular question he repeatedly raised was much narrower than his larger theories. He focused on the physical evidence in ancient stone. If copper and ordinary abrasives were responsible for the precision seen in some Egyptian granite, could experimental archaeology reproduce the same results? And if it could not, was there another abrasive or another technique missing from the conventional explanation? Rather than treating the question as a matter of belief, the approach that emerged was to examine the stone itself at a scale far beyond what the human eye could see. That required a completely different kind of investigation. A scanning electron microscope could reveal microscopic scratches and fractures with extraordinary detail, while energy-dispersive X-ray spectroscopy could help identify the elements present in the material trapped within those features. Instead of simply looking at a granite surface and asking what it appeared to have been made with, researchers could ask a much more precise question: what chemical traces are actually embedded inside the ancient cuts? The distinction is enormous. An archaeologist might examine a stone and interpret it in terms of culture, chronology, craftsmanship, and historical context. A tribologist, a scientist specializing in friction, wear, and surfaces in contact, looks at that same stone differently. To a tribologist, every scratch is evidence of a mechanical event. Its depth, width, direction, edges, and embedded particles can potentially reveal what moved across the surface, how hard it was pressed, and what material was involved in the process. And that is where the reported discovery becomes particularly interesting. According to the account presented by Hancock and his collaborators, microscopic analysis revealed aluminum oxide within the ancient grooves. Aluminum oxide has a mineral form known as corundum, and corundum is extremely hard. On the Mohs scale, it ranks around 9, compared with quartz at 7 and copper at roughly 2.5 to 3. In its gem-quality varieties, corundum becomes ruby or sapphire, depending on the trace elements present. But in an industrial context, its importance is much less romantic. Corundum is a powerful abrasive. If particles of it were deliberately introduced into a cutting process, they could provide a much harder cutting medium than ordinary sand. Suddenly, the physical equation changes. Instead of relying on grains roughly comparable in hardness to the quartz inside granite, a craftsman would be using an abrasive substantially harder than the material being cut. But this is precisely where scientific caution becomes essential. Finding aluminum oxide in an ancient groove would be intriguing, but the presence of a mineral alone does not automatically prove that it was used as the cutting abrasive. Contamination, later repairs, geological processes, conservation work, or other sources would all have to be considered and ruled out. The critical question is not simply, was corundum present? It is, was the corundum present because ancient workers deliberately used it during the cutting process? That distinction separates an interesting observation from a demonstrated technological reconstruction. And that is why experimental testing becomes so important. The proposed answer was to recreate the process. Instead of merely examining ancient granite, researchers could take modern granite, copper tools, and different abrasives and compare their performance directly. Ordinary sand could be tested against crushed quartz, while a corundum-based abrasive slurry could be tested under controlled conditions. The goal would not be to create a spectacular demonstration, but to generate measurable results. How quickly does the cut progress? How rapidly does the copper wear? What kind of groove does each abrasive produce? And what does the resulting surface look like under magnification? If the corundum method produced signatures resembling those preserved on ancient Egyptian granite, the case would become considerably more interesting. And the reported experiments are presented as producing exactly that kind of result. The sand-based method was slow and abrasive, while crushed quartz performed somewhat better but still struggled to reproduce the desired finish. When the corundum slurry was introduced, the cutting rate reportedly increased significantly, while the copper tool itself experienced less destructive wear because the copper was functioning primarily as a carrier for the harder abrasive particles. The important point was not simply that corundum could cut granite. Modern engineers already know that extremely hard abrasives can cut hard stone. The more interesting question was whether such a technique could explain the specific marks and finishes found on ancient Egyptian granite. Drilling provided another dramatic test. Ancient Egyptian stone cores sometimes display spiral markings that have fascinated engineers and experimental archaeologists for decades. A rotating abrasive tool naturally produces a characteristic pattern as it descends into stone, so reproducing those patterns becomes a potentially powerful comparison. According to the account of the experiments, the corundum-based method produced spiral markings on granite cores that resembled the kinds of grooves observed on ancient examples. If independently verified, documented, and reproduced under controlled conditions, that would be far more significant than simply demonstrating that corundum can cut granite. It would suggest that the same basic mechanical process could potentially account for specific archaeological features. Yet even that would not solve the entire mystery. A successful experiment demonstrates possibility, not historical certainty. To establish that ancient Egyptians actually used corundum, researchers would need a broader body of evidence, securely dated archaeological samples, independently verified chemical analysis, evidence for the acquisition or trade of corundum, traces of the material in relevant quarry contexts, experimental reproductions conducted by independent teams, and microscopic signatures that consistently match the ancient examples. The stronger the chain of evidence becomes, the harder it becomes to explain the results as coincidence or contamination. And there is another fascinating implication. If ancient Egyptian craftsmen really did use high-hardness abrasives such as corundum, the discovery would not require us to imagine lost machines, mysterious technology, or an unknown civilization. In some ways, the explanation would be more remarkable precisely because it would be entirely human. It would mean that ancient craftsmen understood a fundamental principle of materials science. You do not necessarily need a harder tool if you can place a harder abrasive between the tool and the stone. The copper does not have to defeat the granite. It only has to hold the particles that can. That is a deceptively sophisticated idea because it transforms the problem from how could copper cut granite into how did ancient craftsmen learn which abrasive to use, how to process it, how to mix it, and how to control it. And that leads to perhaps the most interesting possibility of all. The real technological achievement may not have been a mysterious machine. It may have been knowledge. Knowledge of mineral hardness, knowledge of particle size, knowledge of pressure, lubrication, slurry consistency, tool geometry, and wear. Knowledge accumulated through generations of craftsmen and passed from one specialist to another. If future research confirms the corundum evidence, then the story of Egyptian granite working would become less a story about primitive people somehow accomplishing impossible feats, and more a story about a highly skilled technological culture whose expertise has been underestimated because the tools themselves did not survive. For thousands of years, the stone preserved the evidence even after the tools disappeared. The copper corroded. The abrasive washed away. The craftsmen vanished. Their workshops were buried beneath layers of history. But the granite remained, still carrying microscopic scars from whatever process created it. And perhaps that is why the investigation is so compelling. The answer may not be written on a wall or preserved in a papyrus. It may be sitting inside the grooves themselves, waiting for an instrument powerful enough to read them. If the reported corundum evidence survives independent testing, it would not prove every controversial theory surrounding ancient Egypt. It would not prove Atlantis, a lost civilization, or any other extraordinary claim. What it could do is something far more specific and scientifically valuable. Force researchers to reconsider the technological capabilities of ancient Egyptian stoneworkers and investigate whether sophisticated abrasive engineering played a much larger role in granite cutting than previously recognized. And perhaps that is the real mystery. Not how an impossible machine disappeared, but how an ordinary-looking piece of stone managed to preserve a technological secret for 4,000 years. For generations, researchers have photographed these surfaces, measured these cuts, studied these drill cores, and walked past the same evidence. Yet the crucial clue may have been invisible until someone stopped asking only what the finished stone looked like and started asking what happened to the stone at the microscopic level. Because sometimes history does not hide in the spectacular places. Sometimes it hides in a scratch. And sometimes the smallest mark on an ancient stone can force us to rethink the entire technology behind it. Now, it would be easy to turn this into a simple hero story, and it is not one. Hancock has made claims over the years that have been heavily criticized by archaeologists and historians, and being persistent about one technological question does not automatically make every other conclusion correct. The important thing here is not whether Hancock is a hero or a villain. It is whether the physical evidence can survive independent examination. Because granite does not care who discovered the question. A microscopic groove does not know whether the person studying it has a degree in Egyptology, engineering, geology, or none of the above. The stone only records what happened to it. And if the conventional explanation cannot reproduce those marks under realistic conditions, then the responsible response is not to declare a mystery solved or to declare an entire civilization misunderstood. The responsible response is to test the problem again, more carefully, with better instruments and controlled experiments. That is exactly where the investigation takes a dramatic turn. Instead of continuing the argument at the level of books, lectures, and competing interpretations, the focus shifts downward into the microscopic world, where the stone itself might be able to answer the question. If an ancient tool cut the granite, then it should have left behind a mechanical fingerprint. Every cutting process produces wear. Every abrasive leaves traces. Every material pressed against another creates microscopic scars, fractures, scratches, and residues. The challenge was finding those traces and determining whether they were consistent with the tools traditionally attributed to the Egyptians. And that required a specialist who approached the stone from an entirely different direction, not as an archaeological artifact, but as a record of mechanical interaction. This is where tribology enters the story. Tribology is the science of friction, lubrication, wear, and the behavior of surfaces when they come into contact. It is the kind of discipline used to understand why gears fail, why industrial cutting tools wear down, why bearings overheat, and why one material scratches another. To a tribologist, an ancient granite surface is almost like a crime scene. The groove is the event. The scratches are the evidence. The tiny particles trapped inside the fractures are potential witnesses. By examining their size, shape, composition, and location, a scientist can begin reconstructing the forces that acted on the stone thousands of years ago. The question changes from, what do we think the Egyptians used, to something much more measurable. What material actually left this particular mark? So, the ancient granite was brought into a modern laboratory environment, where instruments could see what the human eye never could. A scanning electron microscope could magnify the surface to extraordinary levels, revealing microscopic scratches and fractures in the stone. Beside it, energy-dispersive X-ray spectroscopy could identify the chemical elements present in selected areas. The combination was powerful because one instrument could show the physical fingerprint, while the other could investigate the material fingerprint. If copper had been involved, traces of copper might be detectable. If quartz had been responsible for the abrasion, its characteristic mineral composition should appear. And if another, harder abrasive had been used, the same analysis might reveal its presence inside the ancient grooves. The expectation, under the conventional model, was straightforward. If Egyptian craftsmen had used copper saws with sand as the cutting medium, then the microscopic evidence should be compatible with that process. There should be signs of abrasive action produced by relatively hard sand grains carried by a softer copper blade. The copper would wear. The abrasive would grind. The granite would gradually disappear. There was nothing inherently impossible about that mechanism. The real question was whether it could explain the particular quality of the surviving stonework. And when the microscope was turned toward the ancient grooves, the investigation reportedly produced an unexpected result. Traces consistent with aluminum oxide. That single identification is where the story becomes genuinely interesting, but also where the distinction between evidence and proof becomes critical. Corundum is extremely hard. On the Mohs scale, it ranks around 9, dramatically harder than quartz and far harder than copper. In its gem-quality forms, it is associated with ruby and sapphire, but its importance here is not its value as a gemstone. Its importance is mechanical. A corundum particle placed between a softer tool and granite could act as an aggressive abrasive, biting into the stone rather than simply sliding across it. In principle, such an abrasive could make the copper tool less important as a cutting instrument. The copper would become a carrier, while the hard particles performed the actual removal of the granite. And suddenly, the old question takes on a different shape. The problem was never really that copper was too soft to cut granite. The conventional explanation already recognized that. The problem was whether the abrasive being carried by the copper was capable of producing the efficiency and precision visible in the ancient stone. Ordinary quartz sand can abrade granite, but quartz and granite already contain similarly hard minerals. Corundum changes the equation. It introduces an abrasive that is substantially harder than the quartz it is attacking. The difference is enormous at the microscopic level. Instead of relying on repeated, relatively weak scratching, the abrasive particles can penetrate, fracture, and remove material more aggressively. The copper no longer needs to win a contest against granite. It only needs to keep the abrasive in contact with the stone. But that discovery creates another question, perhaps an even more important one. If corundum really was being used, where did the ancient Egyptians obtain it? Corundum is not simply another handful of desert sand that could be gathered outside a quarry. A deliberate technological use of it would imply sourcing, processing, transportation, and knowledge. Someone would have had to recognize that the mineral was unusually hard, acquire it, prepare it into a usable abrasive, and understand how to deploy it effectively. That would not be an accident. It would represent specialized technological knowledge. And this is where the story moves away from the idea of ancient workers simply possessing clever tools and towards something more sophisticated, an understanding of materials. The craftsmen would have needed to know that hardness matters. They would have needed to understand that particle size affects cutting behavior. They would have needed to maintain the right pressure and keep the abrasive where it could do its work. A slurry that was too thin could run away from the cutting zone. One that was too thick could clog the groove. The abrasive would need to be continually replenished, and the tool would need to be controlled. In other words, the technology would not simply be the copper blade. It would be the entire system: tool, abrasive, water, pressure, motion, and the accumulated knowledge of how those variables interacted. That possibility becomes especially important when experimental archaeology enters the picture. Because the strongest way to test a proposed ancient technology is not to argue about it, but to attempt to reproduce it. Take granite. Take a copper tool. Test ordinary sand. Test quartz. Then test a harder abrasive, such as corundum. Measure the cutting rate. Measure tool wear. Examine the resulting surfaces under magnification. Look at the grooves. Look at the debris. Look at the microscopic signatures. If one method consistently produces results that resemble the ancient examples, while the others do not, the argument becomes much more difficult to dismiss. The reported experiments involving corundum are therefore important, not because they magically prove how every piece of Egyptian granite was produced, but because they offer a testable mechanism. A corundum-based abrasive can cut granite. Copper can function as a carrier rather than the primary cutting material. And under certain conditions, the resulting wear patterns and surfaces can potentially resemble features observed in ancient stonework. That does not establish historical use by itself. But it turns an abstract objection into a concrete experimental question. Could this have been the missing mechanism?